Section 6.7, Part 3 video. If $800 is deposited into an account paying 9% annual interest, compounded continuously, keyword continuously, how long will it take for the account to increase to $1,300? Round your answer to the nearest hundredth of a year. Now, the equation that we're going to use is A equals P e raised to the RT, right? Looks very similar to the equation that we used previous for decay and half-life. So an exponential with an E has a very similar formulas based on scenarios. So what we have to understand is the P, that's how much we put in. That was initial deposit. We put 1,800. The A is the final amount. We want to, they told us we got $1,300 out of that. And then R is the interest rate. Now that's at 9%, but we have to put that as a decimal. And we're trying to find how long is the time. So here we go, folks. 1,300 equals 800 e to the 0.09t. And the R up here, the rate, is positive because it's going to grow, right? First thing I'm going to do is I'm going to isolate my E, because we know based off previous problems that we've worked in section 6.7, we need to isolate our E so that we can take the natural log of it. So we get 1,300 over 800 equals e to the 0.09t, and then I just take the natural log of both sides, and that cancels that. Now I like to leave the fraction. I don't like to round because it's just going to cause decimal errors, and we just don't need to be dealing with decimal errors. So we're going to do this. We're going to divide by 0.09. Now this looks very familiar because we've been doing it all section long. So again, t is equal to natural log of 1,300 over 800 divided by 0.09. Now I would do the top. I'd take the natural log of 1,300 divided by 800, make sure that that's in parentheses, hit enter, then I would divide it by 0.09. And in doing that, I get 5.394, and it said, I think, 2 hundredths or 2 decimal places, which would be 5.39 years, right? Okay, so that's the setting up of the problem is basically what you're going to do. And even though this one is a money problem, it's very similar to what we've worked continuously within this section. So we got to make sure that what we're doing is recognizing the patterns, even though the problems are changing. The basic underlying solving and tools that we're using are the same. Now, let's go buy a can of Coke. Coke was in 10 cents in 1960, and we've got a model here that says here's the cost of Coke since 1960. When can we expect the cost of Coke to be $1? Well, if you're old enough, you knew that that happened way back when. But we're going to calculate it because this isn't going to give us a correct indicator. So the C sub t would be the dollar, right? So 1 equals 0.10 cents, right? E to the 0.0576t. Now, you should be able to already recognize that, okay, I got an E, I got an isolated. So I'm dividing this cancels. Now what that's going to leave me with is 1 over 0.1, right? I dropped that 0 because it's not significant. 0.576 t. We'll take the natural log of both sides, right? Natural log cancels an e. That's how we undo it. And then 1 natural log of 1 over 0.1 equals 0.0576 t. And then, of course, we are going to set and divide by 0.0576 on the both sides. Now, I'm going to do this right here. I'm going to bring it on up here. So t equals the natural log of 1 over 0.1 divided by 0.0576, and when you get done, you get 1999.9754. And so let's see. It says, in what year is it expected that a can of Coke will cost $1? Well, you could say 1999, but that's not true. In the beginning of 1999, it was not $1. It was actually less than $1. It's actually, if you look at this, it's at the end of 1999 that when it becomes $1. So I'm going to say, because of that, that really if we had just had to pick a year, that the year would be 2000, that it was $1. Now, I think it was maybe more than that, but it could have been. I don't know. I mean, if you get curious enough, you can look it up, see what the cost of a Coke was in the year 2000, and see how close we are. Matter of fact, hold on, I'll do it. Okay, folks, according to Answers.com, it said in 2000, year 2000, the actual price was $1.60. So it just shows that this equation that they have here is only a predictor, not an absolute. And it has to follow inflation and stuff like that. So, all right, so let's go to the next one. Number of airline passengers in 1990 was 46 million. The number of passengers traveling by airplane each year has increased exponentially by this model. Where T's the number of years since 1990. Okay, that's a big clue right there. T is number of years since 1990. So T equals 0 at 1990. That's what that is saying. In what year is it predicted that 900 million passengers will travel by airline? Well, folks, here's the equation. In 1990, it was 46 million. That's where the beginning amount times 1.035. That's your growth rate, that, or your base that they're saying. Now our piece of T right here is going to be 900 because that's what we're trying to find. 466 times 1.035 T. Now note that this one does not have an E in it, right? It's not an exponential with an E. But we're going to still do the same thing. We're going to bring this over, cancel, leaves me a 900 over 466 equals 1.035 raised to the T. And boy, I could write that a lot better. So let me write that a lot better. Now, if it's an exponential, has an E, then we'll do the natural log, right, to both sides. But if it's not, if it's just a plain exponential with a base with a number other than E, and 1.035 is the base, then what we have learned is we can take the log of both sides. So what we're going to do is we'll take the log, because we can't get 900 over 466 to be the same base as 1.035. So we could set their exponents equal to one another. So this works 100% of the time. Now in doing that, when I do the log both sides, I'm going to bring this t because and put it up there in front, the power property of a log. So just know that's why that's going out there. And if you remember back in expanding and condensing logs, then that's where that property shows up. Equals t times the log of 1.035. And of course, folks, this should really start to kind of fall apart. You should see that it's, divide both sides by 1.035. This cancels out. It leaves me with t equals the log of 900 over 466 all over the log of, clean that up, 1.035. Now, I would do the log of 900 over 466, hit enter, and then divide by the log of 1.035. And in doing that, we get a time of 19.1332. Now, that's years, right? That's years, but that's not in the year 19. That's in the year 19 years past 1990, because again, we reset the clock. Everything was measured from 1990. So if we look at this, our real time would be 2009.1332. And again, this goes back to the question we got into with years with the Coca-Cola problem. In the beginning of 2009, there was not 900 million people at the beginning of that year. So it may take 2009, but it didn't get to 900 million until after 2000, somewhere after the beginning of 2009. So you could safely say 2010. So that's what I would put, but if it comes back and says it's wrong, put 2009. But as a mathematician, you can't say it hit something in 2009 in the beginning when it didn't. See this 0.1332? That's a portion of a year. So somewhere in the year 2009, it hit 900 million. So to be safe, you can say, okay, in year 2010. All right, so just kind of remember that. So there you go. A lot of similarities that we're doing. It's not an E as the base, but we still approached it and the process was still the same. We didn't take the natural log, we took the log, right? And if we take the log, then we know we have that power property that has to bring that exponent out to the front, right? So just be mindful of that. Now, here's probably one of the easiest problems that there is. And we're going to work that one plus one more and we'll be done with section 6.7. Suppose that the population of a city is given by the equation P sub t equals 100,000 e to the 0.05 t, where t is the number of years present from the present time. Okay, t is the number of years from the present time. How large is the population now? T is the number of years from present time. Well, we don't know. So we have to assume that T is right now. If it's right now, then here's your initial amount, right? 100,000. Your A sub 0, okay? I don't like the way that this problem's worded. It could have been worded a little bit bigger or better. A little too much ambiguity in this one. But anyway, there it is. Okay. Now, last problem, guys. A bacteria grows according to the formula P equals P sub 0 A to the T. It's nothing more than exponential, right? But there's a couple things we got to do here. This is kind of going back to the beginning problem. If it takes 4 days for the culture to triple in size, how long will it take to double in size? Round to 2 decimal places. Well, we can look. We can attack it a lot of different ways. But the biggest thing that I'm gonna look at is I'm gonna find me a base, because they said, hey, triple means 3, and it has to be in one, every 4 days it triples, right? So when I do that, what that gives me is 1.3161 is my base. Now, why am I putting the 1 over 4? Well, that 1, if you were to put it in an equation, would be days. So until it hits a multiple of 4s, it doesn't triple, right? So that's why you have that 1 up there, because it'll be 1 times the number of days. It's not going to change anything. So that's kind of where that's come about. So here's my base, right? So what we're going to do is we'll set it up. We'll say P equals P sub 0 AT. Well, they got A, but we're going to say BT, right? The base. We're going to say this. We're going to say begin amounts 2, end amounts 4. That's doubled, right? Here's my base of 1.3161 based off the scenario that we have. T, we got to find how long will it do. And of course, if we divide both sides by 2, we get the ratio of the ending over the beginning to be 2, which means it doubled. And then we have 1.3161 raised to the T. Now this leads us right back to previous problems, right? It's an exponential. It's not an E, but we're going to solve it by taking the log of both sides. Okay. And by taking the log, we're going to move that T out here because of the properties, right? The power property of a log. So what we're going to get is the log of 2 is equal to T times the log of 1 point. Well, let me do this. And then we're going to divide both sides by the log of 1.3161. And what that's going to do is cancel. And then it'll leave me what time is equal to the log of 2 divided by the log of 1.3161, right? Put some parentheses in there. So time is equal to 2.5235, which if it said to 2 decimal places, time would be equal to 2.52 days. So if it takes 3 days, no, 4 days to triple, it takes 2.52 days for it to double. Okay, so there you go. This ends the part 3, section 6.7.